Okay, so now we're going to look at particle motion problems. So you're going to pause the video here and you can read this stuff that I have leading up here. But to sum it up, we're talking about moving along the x-axis or like a horizontal motion. So pause the video and read that. Okay, welcome back. So, in this lesson, we're going to develop the ideas of velocity and acceleration in terms of position. So we're going to speak of two types of velocities and accelerations. Let's define average and instantaneous velocity in the box below. So I'm going to say, whoops, I need a pen here. Suppose, just a little bigger, P of t is a function which defines the position of a moving object at time t. The average velocity over a time period, over a time interval, is equal to the average rate of change of position. Which is equal to the position at time A minus the position or the location at time B, all over the difference in that interval, the change in time. So it's change in position over change in time. What we really need to note here is all the other times we talk about the derivative or the average rate of change or whatever we're talking about, we'll say the rate of change of whatever the thing is. If we're talking about temperature, we'll say the rate of change of temperature is the derivative. The average rate of change of the temperature would be the slope of the secant line. The point here, though, is that if we're talking about temperature, we call it the rate of change of temperature. For position, we don't really call it the rate of change of position. When we talk about the rate of change of an object's position, we have a new word for that, velocity. So you have to think of velocity as really meaning rate of change of position. It's got its own word. For rate of change of position, this is one of the things where we don't call it rate of change of position, we just say it's the object's velocity. So that's going to tip you off that it really should be the rate of change of position should either be the secant, the slope of the secant line, or the slope of the tangent line, depending on whether we're talking about the average velocity. So if we're talking about the average rate of change, we're talking about secant line. I should say slope of a secant line over that interval. Or if we're talking about the instantaneous rate of change of position, which is also called velocity. I need an S in there, don't I? Hopefully you cannot hear that awful Italian music in the background that my family's listening to in the other room right now. They're like YouTubing rye and watching Italian music. It's awesome. Well, this is a lowercase p. So the instantaneous velocity is going to be the slope of the tangent line at A, at that specific point. All right, so we really want to talk about average velocity versus instantaneous velocity. So a particle's position is given by the function p of t, blah, blah, blah. So we have some function here, and that's the position. Remember, the particle's not moving along that curve. That's just telling you where it is on the x-axis. Answer the following questions. What is the average velocity on the interval from 1 to 3? So when they're asking about average velocity, we're talking about the slope of the secant line. So we want to do p of 1 minus p of 3 all over 1 minus 3. So that's going to be our average velocity. I'm going to write it like this. Like subscript. The average velocity would be that, which is 0.274 centimeters per second. You got to have your units on it. We're talking about a rate of change now, so we've got per in there. And these are calculator active because we're kind of doing it with this function. Let's get some practice in here with our calculator to do these. What's the instantaneous rate of velocity of the particle at time t equals 1.5? So now they want the instantaneous velocity at a specific time. So that means what we're really looking for is the derivative at 1.5, the slope of the tangent line at 1.5. So you can do this on your calculator and get 4.787 centimeters per second. Right? You would put the original function in y1, then go back to your main screen and do n derive at 1.5, and you should get this. Let's go ahead and do it by hand anyway. I think it's good practice to calculate this derivative. So we're going to take p of t, the position, and we're going to take the derivative of it. This is product rule. So the derivative of the first is e of t times recopy of the second plus recopy of the first times derivative of the second. So now we want to evaluate at 1.5, and so now it's going to be e to the 1.5 times sine of 1.5 plus e to the 1.5 cosine of 1.5, and that should get you that same 4.787 centimeters per second. So let's move on here. Sorry, I just got a low battery message on my computer. I'm going to pause this and plug it in. Give me a sec. Okay, so moving along here. So when you're given a function f, how do we find the slope of the secant line on an interval from a to b? We had to do the slope of the secant line, which I talked about before. So we just want to kind of highlight these connections. The slope of the secant line correlates to doing the average rate of change over an interval. The change in y over the change in x. Remember, f of a means the y value for a. F of b means the y value for b. That's the slope of the secant, and that's going to be equal to our average rate of change of position, or in this case, velocity. Because rate of change of position, we name it and we call it velocity. And the slope of the tangent, now we just need to add a single point, instantaneous rate of change. That's going to be equal to the derivative at that point, whatever it is, let's say a. And that's going to be what we call the instantaneous. You did that part. Oh, I have to say it again. I can't spell. I'm so sorry. Jenna, stop laughing at me. Average and instantaneous acceleration. So now we're going to talk about acceleration. So now we know we're going to say if we have this function p of t is position and p prime of t is what we now know to be velocity. I guess they've turned up the music upstairs. We're going to apply this idea now to acceleration. The average acceleration is, if we take on an interval a to b, if we do the velocity of a minus the velocity of b, we're going to do the slope of the secant line of the velocities. That would give us our average acceleration. Keep in mind, acceleration now is a word we use to mean the rate of change of velocity. So When I'm talking about the rate of change of velocity, if I'm doing an average rate of change, I'm doing a secant line. I should say slope of a secant line of the velocities. So then our instantaneous acceleration is going to be the derivative at a certain point of velocity. And that's really the second derivative of position. And that's going to be the slope of the tangent line. So what we're saying here, really, the thing to note is rate of change of position is velocity, and the rate of change of velocity is acceleration. We have names for them. So acceleration can be looked at as the rate of change of velocity, or the rate of change of the position, the second derivative of position. So velocity is the derivative of position, acceleration is the derivative of velocity. All right, so let's move on here. The particle's position is given by the function position, so we're staying with that with that same position function. And P of t is measured in centimeters, and P is measured in centimeters, and t is measured in seconds. So what's the average acceleration on the interval 1 to 3? So we know that from before, our derivative function, which is really now we know our velocity function. If we factored out the e to the e of t, e to the t, we know that we had, I think it was sine of t plus cosine of t. Yeah, right here, if I factor out the e to the t, I'll have e to the t times sine of t plus cosine of t. That's our velocity function. So if we want to find average acceleration, we're going to do the velocity at time 1 minus the velocity at time 3, and then over that interval, the change in time. That's going to give us negative 10.403 centimeters per second squared. Okay, so we have to know our units here for acceleration. That's the average acceleration over that time period. And remember that really why it's centimeters over second squared, it's because it's a velocity on top, and a velocity is measured in centimeters per second, and then on the bottom it's measured in seconds. So when we have velocities up top, we have centimeters per second, and then we're dividing by another second, some more time here, dividing by more units of time. That's how we get centimeters per second squared, right? Because if I simplify this complex fraction, I would multiply by 1 over seconds instead of dividing by seconds, and I would get centimeters per second squared. So that's a way to think about it. What's the instantaneous acceleration of the particle at time t equals 1.5? So, and by the way, obviously I'm just I've already worked these out, plugging in 1 into the velocity function. You should pause the video and make sure you can get these numbers. The instantaneous acceleration, we can use our calculator. We, again, know the velocity function. To be this. So then on my calculator, I can do n derive at 1.5 and get my instantaneous acceleration. At the moment, 1.5 seconds. And that would be let's go through the motions. It's good practice to do it without our calculator. So we've got to do the derivative of velocity. Again, we have product rule, so the derivative of the first is e to the t times recopy the second plus recopy the first times derivative of the second. So the derivative of sine is cosine. The derivative of cosine is negative sine. So then if we common factor out in e to the t, I've got sine of t plus cosine of t. I'm just gonna, I'm just gonna leave it out as, because we're plugging in 1.5 anyway. So it's e to the 1.5 times sine of 1.5 plus cosine of 1.5 plus e to the 1.5 cosine of 1.5 minus. So you do that whole thing out, and you should arrive at your 0.634 centimeters per second squared. All right, so let's kind of summarize what we're talking about here, and I've already sort of talked about it, but let's write it down. So we know that if f of x corresponds with the position function, right? So if we have our first function, like we can think of our position as our original function, then we know the derivative of that function would correspond with the velocity function. So what we're really saying here is the derivative of our position function is velocity. And then if we take the derivative of that, it's really the second derivative of our original function. It's the first derivative of our velocity function, and it's called a of t, which is our acceleration. And since we're talking about derivatives here, well, I'll leave that as is. I'll leave it at that. So this is just really kind of summarizing that the derivative of position is velocity, and the derivative of velocity is acceleration. Because derivatives are rates of change, and the rate at which something's position changes, we call that velocity. And then the rate at which something's velocity changes, we call that acceleration. So we'll do some more summarizing here. And then we can do some problems, some practice problems. So when the velocity is equal to 0 or is undefined, we have a potential change in direction of the moving object. Okay, so whenever velocity is 0 or undefined, the direction of the object could be moving. That's because the position reaches a local maximum or minimum. So remember, we're moving only horizontally. So that means it's gone as far left as it's going to go for that little moment in time. Because remember, we're just talking about a relative extrema. So it has a potential to be, it stops, because when the velocity is 0, it stopped moving, and then that means it may turn back around and go the other way. Keep in mind that it could stop and then continue going in the direction it went to. That's why we say potential. It's all related back to maximums and minimums, right? Whenever velocity is 0, we have a potential max or min on the position, meaning a maximum being furthest right and a minimum being furthest left. That's how I think of it. Okay, so when the velocity is positive or bigger than 0, then that means our position of the particle is decreasing. That means the particle is moving. Oh, that should be increasing because we're bigger than 0. Sorry, position is increasing, and that means we're only talking about left and right, right? So that means if our position's increasing, getting bigger means a rightward direction. So that means the particle is moving to the right. When our velocity is less than 0 or negative, it means vice versa, that our position of our particle is decreasing. And decreasing in leftward and rightward motion means that the particle, that's supposed to be an arrow, that means like both of these things mean each other, biconditional. The particle is moving to the left. This is tied into what we know about a function and its derivative. Okay, we know when the velocity changes from positive to negative, that means that the particle has reached a maximum. So that means the particle changes its direction, basically, moving right to moving left. Right, when its velocity changes, positive velocity means that it's moving to the right. Negative velocity means it's moving left. So the time from when it changes means it stopped and changed its direction. So then vice versa, particle changes moving left. Changes, I should say, from moving left to now moving right. All right, and these, again, we'll talk about it more as we do the problems in class, but these are obviously related to the whole idea that when a function's increasing, f prime is positive, and there's a max when f prime changes from positive to negative and things like that. Acceleration, now we're looking at basically the connection between acceleration and velocity. And remember that acceleration is the derivative of velocity. So again, these are going to sort of be closely related to when a function is increasing, f prime is positive, and all the stuff that we know about a function and its derivative. So if the acceleration is 0 or undefined, that would mean like a derivative is 0. That means the original thing has a potential change in sign of velocity. So we're going to say that the velocity, there is a potential no, this is not that's not what I want to say. When acceleration is 0 undefined, there's a potential extrema of the velocity. So say a potential max or min velocity. When the acceleration is positive, then we know the velocity is increasing. We know when acceleration is negative, then the velocity is decreasing. We know that when acceleration changes from positive to negative, the velocity changes from increasing to decreasing. When the acceleration changes from negative to positive, then we know that the velocity changes from decreasing to increasing. We could also say on these last two that the velocity has a maximum and the velocity has a minimum. But we're going to think about it more as have the velocity increasing and decreasing. All right, so the graph below represents the position of a particle. So that's a position function, which is moving along the x-axis. It's important to remember that the particle is not moving on this curve. That just represents its position over a given time. The particle is moving back and forth on this axis. And remember, it could stop and go back. So it could go this way first, then after like 3 seconds, turn around, come part of the way back for a second, right? And then turn back around and go that way, and then come all the way back here and then go back. So it can go back and forth. But it's moving, that's what's happening. It's moving along the x-axis, all right? So at which point is the velocity equal to 0? Justify your answer. So we know that velocity is the derivative of position. So I could think of this as, when is the derivative equal to 0? Anywhere there's a max or a min, the derivative is equal to 0. So we're going to say that the velocity is equal to 0 when t equals b and t equals d, because the position function changes direction. I could say because The way that I found it also is I could say because the position function has a maximum, a local maximum, and a local minimum. At which points does the acceleration equal 0? So now acceleration equaling 0 would be when the derivative equals 0, or we also know acceleration equaling 0. Acceleration is the second derivative, so we know that on the original graph we would have a point of inflection. So it looks like our point of inflection where concavity changes, right? Because we have negative acceleration on that green interval, and then we have a positive sign for acceleration on the purple interval. C is where it switches. So the acceleration equals 0 at time C. That's a lowercase t. Because the position function has a point of inflection. On what intervals is the particle's velocity positive? So that means velocity is the derivative of position. And so that means that the interval where the velocity will be positive is what we're looking for, right? That's going to be anywhere where the function is increasing. And so we're going to say, let's see, do we have any kind of an interval on here? We're going to assume time can't be negative since we're talking about time. So the velocity is positive on the interval 0 to b, and again from d to infinity, because the original position function is increasing. That's because we know velocity has to be the derivative of position. So we're looking at the graph of the position. So anywhere the position graph is increasing, then the derivative is going to be positive. Okay, on what intervals is the particle's velocity negative? So we'll say that velocity is negative on the interval from b to d, because that's when the position is decreasing. And by the way, I used p to be my position function in the notes above. A lot of times s of t will be used to represent position function s of t. On what intervals is the particle's acceleration positive? So the acceleration of the particle is positive on the interval, let's see, c to infinity, because the original function is concave up, and we know that second derivative is positive when the original is concave upward. So when we have a position function, concave up means positive acceleration. We can talk about what that means in class, why that's happening. On what intervals is the particle's acceleration negative? So the acceleration will be negative on the interval, let's see, 0 to c, because the original function is concave down. All right, so let's kind of summarize what's happening here. We're going to call these, I guess, the 5 commandments of particle motion. And we're talking about horizontal movement, let's recall. All right, so the first one, these are the things we're going to kind of use the most to solve problems. If the velocity is positive, then the object is moving to the right. Sounds like Andrea Bocelli up there. It's getting bad. They're getting into Bocelli. If the velocity is negative, then the object is moving, got a couple eyes in there, to the left. The speed, which we haven't talked a lot about, is increasing when the signs of velocity and acceleration match. I'll say are the same. The speed is decreasing when the signs of velocity and acceleration do not match. And then lastly, if the velocity is equal to 0, but the acceleration is not equal to 0, then the object is momentarily stopped and is changing direction. All right, so let's look at an example. Suppose the velocity of a particle is given by, well, how much time are we here? Do I continue the torture? 33 minutes? Yeah, we got another 10 minutes. We'll just do this example and I'll stop. I will not make you do these guys in the video, these upcoming AP questions. We'll save those for class. All right, so suppose the velocity of a particle is given by the function there. For t is bigger than or equal to 0, so we're not going to have negative time. T is measured in minutes, and v of t is measured in inches per minute. So we have our velocity function. Answer the questions that follow. All right, so remember, we don't have our position function here. We have our velocity function. All right, so find the values of v of 3 and v prime of 3. Based on these values, describe the speed of the particle at t equals 3. So v of 3 equals 3 plus 2. What's the function? Times 3 plus 4 squared. That's going to be equal to 5 times 7 squared. 5 times 49. 5 times 50 is 250, and then I got 5 ones I got to take off of 245, and that's going to be inches per minute. We're talking about a velocity here. So there's one of our answers. There's v of 3. V prime of 3 we've got to do product rule on this guy. So first let me do v prime of t. Okay, so we got the derivative first is 1 times recopy the second, recopy the first, times the derivative of the second. So we have to do chain rule on this. So that's going to be equal to t plus 4 squared plus 2 times t plus 2 times t plus 4. Because inside there we're going to have, what, 2t plus 8. I can factor out the 2, call it t plus 4. So now we're going to plug 3 into that. I'll let you pause the video and do that. We're going to end up getting, so welcome back, we're going to end up getting 119 inches per minute per minute. All right, so that's our other answer. So since v of 3, the velocity is positive, and the derivative of velocity, which is acceleration, is positive, then the speed of the object is increasing at time 3. That is, let's see, the speed is increasing when the signs of the velocity and acceleration are the same. That's our third commandment. On what intervals is the particle moving to the left or moving to the right? Show your analysis and justify your answer. So if I look at my commandments, I know that the object's moving right when the velocity is positive and left when the velocity is negative. So I just need to figure that out. So I want to find out, first of all, when the velocity is equal to 0, because that could be a potential change in direction. We don't have to do any derivatives or anything. We already have our velocity function. We know our velocity function is going to be equal to 0 when t equals -4 and when t equals -2. And they gave us the interval 0, right? Time cannot be negative, so we're starting for all time bigger than or equal to 0. So really, we just have to test this interval right here with our velocity and find out if it's positive or if it's negative. So if I plug, say 1 into my velocity function, I get a positive times a positive. So that means that the velocity on the interval t is bigger than or equal to 0, the velocity is always positive. So the particle is always moving to the right. And that'll do it for our notes.